like what I did for you yesterday on your on your notes.
Except they don't.
Was there a stinger that they threw in there? 53, you only had to do A. HNO2, they want to know the major species present, and then calculate, yes, so calculate the pH. So to calculate the pH, well, here's the major species present, H plus NO2 minus HNO2. 3 species, okay? All right, and then in this case, real fast, just 0.250, 0.250 molar was the, basically, when they give you that, it's really, like I mentioned yesterday, that's really the equilibrium concentration because these are small acids and bases, so they don't dissociate very much, okay? Because they're weak acids and weak bases. Right now we're doing acids, but we'll do bases starting today. Yeah. So this is an acid. This is the dissociation of nitrous acid. And so calculate the pH. Did they give us, look at that, they didn't give us the Ka.
Exactly.
Wow.
I'll agree with you.
Well, guys, you didn't even,
It's on the chart.
and didn't I tell you on your notes that it was on there?
It told me yesterday.
Yeah.
Page 628? Yeah, there's a chart on page 628 with all the Kas. You know, that's a poor excuse for not doing your assignment because obviously you know there's going to be charts in here because I even mentioned it on your notes. So the Ka for HNO3, HNO2, there it is, 4 times 10 to the minus 4, right? So 4 times 10 to the minus 4 is equal to
X squared.
yeah, let me just show the extra step. Just to make the chemistry gods happy, okay? So there's what we're plugging into. It's going to be x squared. It's always x squared over 0.250. 250. So you're going to solve for x, take the square root, and x comes out to be, somebody tell me quick, oh no, that's the pH. The x is 0.01. So x comes out to be 0.0100 moles per liter, which is going to be the H plus concentration. So the pH is going to be the negative log of that, which is 2?
Yep.
2.
Yep.
To be technical, 2.00. Because there's, well, actually 2.00. Oh, but, yeah. I'm not picking on that yet. Amy.
In the back of the book, for the major species or whatever, it said that it was HNO2 and H2O. How come they didn't dissociate it?
They're stupid.
HNO2 and H2O. I mean, yeah, we know there's H2O in there, we just don't include it. They're being real picky. Notice how small this value is. That means there's very little of this and very little of that. So that would make them minor species. There's a lot of water and a lot of HNO2. That's why. I would never be that. But I'm glad you brought that up because that's why. Okay. So there's really 4 species present, 2 of them major, 2 of them minor. Okay.
And we don't care about one.
Only when we're thirsty. All right. Then we care a lot. 62, how are we doing on 62? I got it laid out, if you had trouble with it, that it's right there. And then I gave you 63A, 64A, and 65. Here's 63A. Now, we didn't talk about percent dissociation, so let me just take a moment. Calculate the percent dissociation of 0.5 molar acetic acid. The Ka is given. All you do is it's a formula. That's why I didn't take the time to go over with you because it's kind of like doing so many other things you've done this year. Percent error or percent, I guess it would be more like not percent error, but percent accuracy. And same formula. So if the percent dissociation is it's the amount dissociated, usually for an acid that's going to be the H plus concentration. divided by the original concentration times 100. So in this case, it was, we were solving for the percent dissociation, and it said that, what we did was we solved for H plus, because it's an acid. We were given the Ka, x squared over 0.5, just like we were doing over there. I didn't take the time to write out this one. So we solved for x, which is the H plus concentration, 0.0030. That's how much dissociated, okay? We also got 0.0030 moles per liter of the acetate ion, but we don't care about that. All we care is this is an acid, we just care about the H plus. So that would be a minor species, okay? So 0.0030 divided by 0.5 times 100 is 0.6. Okay, that's all there is to percent dissociation. 65 tried to play with you and make it hard on you and say, if the percent dissociation is 3%, what's the Ka for a given acid? Well, they can't fool us because we know amount dissociated divided by initial concentration. They tell us the initial concentration is 0.15. So we solve for H plus, which is the amount dissociated, 0.0045. Then, since we don't know what the acid is, I just call it HX. It breaks up into H plus and X minus, okay? Ka is, B squared over that. We know it's 0.15, so we just solve for what's in blue there, or we use what's in blue to solve for that. So the H plus concentration is 0.0045. And then you just plug in and you get the Ka for that weak acid. So, talk to me, any other questions before I get into the new stuff? We're going to swing to the base side.
Why is X equal to neutral?
Because, on this one in particular, because we've got some acid, that's what it's just a generic acid, HX. And when it breaks up in water, you get H plus, X minus. So, whatever, these are always going to be the same because they're 1 to 1. So, this is going to be the amount that dissociates. For an acid, it's just going to be, I mean, we could have chosen either one. Either one is the amount that dissociates. So, if this is 0.15 moles per liter, the amount that dissociates is 0.0045 of this and of this. We just picked the H plus because it's an acid. Okay? Now on the base, we'll pick the other thing because that's something later. Okay. Any other questions on anything that you have to do at all? Yes?
For number 64, it says to use the K values on table 14.2.
Yes.
Nitric acid is an element.
Right. That's why I gave you that one. Because I knew the other two you could do that. Nitric acid is a strong acid if you just took a quiz on that, which means it doesn't have a K value. So in that case, whatever the concentration is they give you, 0.20 moles per liter, that's how much H plus you get. There's nothing to do. That's the fun part. So you just take the, what do you got to do on that one? So you just take, so in fact, you don't even have to do any math. Because anytime there's a strong acid, how much of it is going to dissociate? There's your answer, 100%. So it's good when you get strong acids, and that's why I wanted to try to get you to learn them so that you can recognize them. So yeah, when you're doing these problems, before you do anything, think, is this a strong acid or a weak acid? That's important. Okay?